Hello and welcome back once again. So we have been talking about metal matrix composites through the past few lectures, and in the previous lecture we started discussing about the fracture behavior of such composites. So we talked about the fracture behavior of fiber reinforced composites or continuously reinforced composites. But the composite material can also be reinforced by discontinuous reinforcements such as particles. So let us also talk about the fracture behavior of discontinuously reinforced metal matrix composites. These are also known as DRMMCs in short. Okay. So there could be significant difference between the fracture behavior of these two types of composites simply because the reinforcement geometry is completely different, right? In one case you have continuous fibers, so you mainly have to look at the interface bonding, okay, the bonding between the fiber and the matrix at the interface. Here also for the DRMMCs, discontinuously reinforced MMCs, the interface bonding is important, but there could be other modes of failures that you need to consider. So since it is a discontinuous kind of reinforcement in the matrix, the fracture can happen in a similar manner as in the unreinforced metallic matrix. Okay. Therefore, it will be good to first discuss about the fracture behavior of the metal to be able to compare it with that of the metal matrix composites. Metals are generally ductile and fail in a manner which reflects the ductility. So let us first talk about the ductile fracture in metals. When a metal is loaded in tension, it will elongate. Which will lead to a localized reduction in the diameter or cross-sectional area. This is a phenomenon known as necking. So, the ductile fracture in metals is generally preceded by the necking phenomenon. Okay? And necking generally happens at the maximum load. Alright? So, an ideal plastic material which does not go through any strain hardening would become unstable when subjected to tensile loading as soon as the yielding begins. Okay? But in metals, generally strain hardening will occur. And therefore, there will be two competing phenomena that will occur during the tensile loading of a metal. Okay? One is of course the reduction in the area, as I said, which will result in the decrease in the load bearing capability of the metal, and the other is strain hardening, which will increase the load bearing ability of the metal. Okay, so these are two competing factors which will simultaneously occur as the metal is being loaded. Okay, so the instability will occur, or the necking will begin, when the increase in stress due to the decrease in the cross-sectional area becomes greater than the increase in the load bearing ability of the material due to strain hardening. Okay, and this can be written as an expression mathematically by this equation, where P is the load. Okay, so as I said, there are two competing phenomena occurring. One is leading to an increase in the load bearing ability of the material, that is the strain hardening, and another is resulting in the decrease in the load bearing ability of the material, that is due to the reduction in the cross sectional area. Okay, so that can be represented as dP, that is change in the load, equals to 0. Okay, so now we know that P is equal to sigma into A, where sigma is the stress, or in other words, stress is equal to the load divided by the cross sectional area A. Okay, so if we differentiate this, this is what we will get. And according to the instability condition, this is equal to 0, as we have already defined before. Okay, now the volume remains constant, that is L into A, where L is the length, is constant, and from here again by differentiation we will get this. Okay, and dl by L, this is nothing but d epsilon, where epsilon is the true strain. Okay, so now let us see from the instability condition what we get from here. So this is the instability condition. Okay, and if we rearrange this, this is what we will end up with. And just now we saw that this is equal to d epsilon, and therefore we can say that at the point of tensile instability, d sigma by sigma is equal to d epsilon or in other words, d sigma by d epsilon is equal to sigma. This is the instability condition in tension. Alright. We can also obtain the true strain at which this occurs if we consider this equation between true stress sigma and true strain epsilon. They are related by this equation, and from here we know that the strain hardening exponent n is nothing but the slope of the plot between log sigma and log epsilon. That is, n is equal to d log sigma by d log epsilon. That will give us this expression in terms of d sigma by d epsilon, and by rearranging we can also write that d sigma by d epsilon is equal to n into sigma by epsilon. Okay, and now if we put this into the instability criterion, then this is what we will get. Okay, so this is our instability criteria. Okay, and now we have got d sigma by d epsilon is equal to n into sigma by epsilon. So from here we can get the true uniform strain at which the necking will begin. Okay, so the true uniform strain epsilon u is nothing but the strain up to the maximum load. Okay, so if we put this over here, we will get the true uniform strain at which the necking begins is equal to the strain hardening exponent n. Okay, so this is an interesting relationship. So when the strain hardening exponent becomes equal to the uniform true strain in the material, the instability in tension starts, or in other words, the necking will begin. This can be also represented graphically if we plot this equation along with the true stress strain curve. So the true stress strain curve will look like this. And if we plot this equation now on here, it will look like this. So the intersection of these two curves will be the point of instability. So this curve is between d sigma d epsilon and epsilon, and this point is the point of instability. Therefore this will be the uniform true strain, and at this point we know that d sigma by d epsilon will be equal to sigma. Okay, so this is how this instability criterion can be represented graphically also. It can also be expressed in terms of the engineering strain. So if E be the engineering strain, that is nothing but L minus L naught divided by L naught, where L naught is the initial length of the tensile sample. So now if we go by this, we can write it in terms of this also. By bringing in the engineering strain E, so dE can be written as dL by L naught. Similarly, d epsilon is dL by L. And this whole thing is equal to 1 plus E. If we reorganize this, you would end up with this 1 plus E, right? And this is equal to sigma according to the instability criterion, right? So this gives us d sigma by dE equals to sigma by 1 plus E. And this gives rise to an interesting construction if the true stress is plotted against the engineering strain. Okay, so if that is done, the curve will look like this. And let's say here A is a point which represents a negative strain of 1. Okay. Now if we draw a tangent from this point A to this curve, that will give rise to a point on this curve which will represent the point of maximum load. Because at that point, as you could see from here now, the slope is, that is, d sigma by dE is equal to sigma by 1 plus E. Okay, that's what you can see from here. So by representing this in terms of the engineering strain, you can also obtain the strain or the load at which the necking will begin. Alright. So now let us see what exactly happens when the necking starts and how does the material eventually fail. Okay. So let us see what is the mechanism of that failure. So when the necking starts, it will lead to the introduction of a triaxial state of stress around that neck region, as you could see from this particular drawing over here. Okay. And due to the introduction of this triaxial state of stress, voids will be nucleated around that region, as you could see from the second image over here. Okay, tiny voids or cavities will nucleate around the neck region. Okay, so as the material is strained further, as the straining is continued, these voids will grow and coalesce together, leading to the formation of a crack at the center. Okay, so the void coalescence, or rather void nucleation and coalescence, leads to formation of a central crack, as you could see over here. And when you talk about void nucleation, voids generally form at sites like inclusions, second phase particles, or fine oxide particles present in the material, and also at the grain boundary triple points. So once this central crack forms due to the coalescence of the voids, this crack will grow as the material is being strained further, and eventually it will lead to fracture. So as the straining continues, this crack will grow and eventually this will lead to the fracture. These two parts will get separated from each other. Okay. So this crack propagates roughly at an angle of 45 degree to the axis of the sample. Okay. And if you see the finer details, the fracture process first occurs locally at narrow bands of high shear strain. Okay. And these shear bands are located roughly at some angle close to 50 to 60 degree to the transverse direction. So along these bands, sheets of voids are first nucleated as the material is strained. Okay, and these voids will grow and coalesce as we have discussed before, leading to local fracture of the void sheet. Thus the crack growth in ductile fracture essentially occurs by a process of void coalescence. Okay, and this coalescence occurs by elongation of the voids and elongation of the bridges of the material between the voids. Okay, so looking at the finer details of this void nucleation and coalescence, we can say that the coalescence occurs by elongation of the voids and the bridges of material between the voids. So if you look at the fracture surface, you would actually find these elongated voids. But this can be seen properly under an electron microscope like scanning electron microscope. Because the fracture surface is quite rough, and therefore in order to see it as it is, you cannot really use optical microscope, which needs a polishing of the surface and all that. Okay, so if you take the fracture surface and observe it under an electron microscope, a scanning electron microscope, you would see these voids. Okay, so let me show you how does it look like when you observe it under the ACM. Okay, so this is how the voids will appear in the fracture surface when the material goes through a ductile fracture. So you can see the voids all over this fracture surface, right? So this is an indication that this fracture happened by a ductile mode of failure, or this is a ductile fracture. And if you look at the fractured pieces, they would look like two pieces as if they are a cup and cone pair. Okay, so that is why sometimes this is also known as cup cone type of fracture. So if you see it over here, this portion, for example, looks like the cup portion, and this is more like the cone. Okay, so that is why this kind of fracture is also referred to as cup and cone fracture. So when you have a macroscopic observation of the fractured surface, and if it occurs by the ductile fracture mode, you would see this kind of features looking like a cup and cone pair. And on the microscopic level, when you put it under an electron microscope, you would see these voids, which will indicate that it occurred through the void nucleation and the coalescence process, which is a characteristic feature of ductile fracture. And with that, we come to the end of this lecture, but there is more to come. Keep watching.